Hey guys, in this lesson we're going to be studying momentum, which also will cover the concept of impulse. This is the bookwork associated with the lesson. We'll do it in class, but I do want you to have one page for your Cornell notes and the other page for classwork. And the first thing you could write for your classwork is this aim, what is momentum, and then the question numbers for your bookwork. And I'm going to show you a couple of videos now. So I do want you to answer these two questions. I'll have an interactive part of the video for you to record your answers. Alright, so momentum is the product of an object's mass and velocity. So, in other words, if you have an object that has mass and it's moving, then it also has momentum. And the equation for momentum is P equals mv. Mass would be in kilograms, v is going to be meters per second, and the unit for P then is going to be kilogram meters per second. You can see that here. Let's do a very simple question. What's the magnitude of the velocity of a 25 kilogram object that has a momentum of 100 kilograms per second? So I want you to label the variables in your notes and then solve for velocity. So I went ahead and did that here and here. And this is the standard equation for momentum. And I do have a value for P and a value for M, and I just need a value for V. So I'm going to rearrange that. I got the value for V is going to be P over M, so I'm ready to plug in values now and solve. I ultimately got 4 meters per second as the velocity of the object, and they did only ask for magnitude, so I don't need a direction here. In the final question, it seems to be conceptual. It just says, why does the truck have more momentum than the roller skate? So roller skate down here, truck here. Assuming they're moving at the same speed, the truck has more momentum because it has more mass. And you can see in the equation P equals mv that there's a direct relationship between momentum and mass. So associated with momentum is another concept called impulse. And the equation for impulse is going to be J equals net force multiplied by time. Net force is going to be in newtons, time is going to be in seconds, which means that the unit for impulse is going to be a newton second. And you'll also notice in your reference table that impulse is equal to something else. It's equal to a change in P, or a change in momentum. And if you can go back to the videos at the beginning of the lesson, or even just visualize them, you'll probably realize that there was a force acting on the two golf balls, and it wasn't an instantaneous force. It acted over a length of time. So you have the force on the golf ball for some length of time, and that, when you multiply those two things together, that is what impulse really is. Or another way to think about impulse is that impulse is what causes momentum to change. So if you have like a truck rolling down a highway, it has momentum because its mass and velocity are present. But if it hits a rock and suddenly stops, then what the rock did is the rock provided an impulse to the truck, which was able to change the truck's momentum. So impulse and a change in momentum are equal, however, they're not exactly the same thing. Momentum is mass and velocity, the product of those two things, and impulse is what has the ability to change the momentum of another object. Fun fact, the direction of the impulse imparted to an object is the same as the direction of the object's change in momentum. So whichever way the object changes its momentum, that's the same direction as the impulse. Okay, so here's an example question that utilizes the concept of impulse. A constant unbalanced force acts on an object for 3 seconds. So we have a force and we have a time, producing an impulse of 6 Newton seconds east. So the impulse we know now, it's 6 Newton seconds east, and we know a discrete value for time, it's 3 seconds. So it's going to be easy to solve for force in this case. And I also want the magnitude and direction of the force, so you'll need to utilize this particular concept that the impulse is the same as the direction of the object's change in momentum. So I will start by putting in the equation. And since I'm actually going to be solving for the net force, I'll rearrange for that now. And I'll plug in values for impulse, which is 6 Newton seconds east, and time, which is 3 seconds. Which of course yields a value of 2 newtons. And that does meet the requirement of this question for magnitude, but for direction, just know that the impulse is Newton seconds east, and therefore the force would also have been east. On this slide, I'm going to give you a little bit of real-world application. If you've ever played baseball, you maybe have received advice from someone when hitting the ball, and one common piece of advice is to follow through with a hit. So when the bat contacts with the ball, instead of sort of stopping the bat at that moment, it's best to continue your swing. And one of the reasons why that's a very important piece of advice to follow is because when you continue your swing instead of stopping short, you are maximizing the amount of time that the bat is in contact with the ball. So since impulse is F net times time, if you can really increase this amount of time, then you're also going to increase the impulse. And that's going to provide, of course, a much larger change in momentum for the ball. And that's a good thing. It'll travel farther if it has more momentum. Additionally, you maybe have gotten advice when catching a ball, which is when the ball hits your glove, instead of holding your glove firmly in place, it's much better for your hand if you sort of move backwards with the ball and sort of give with the ball as you catch it. And that'll reduce the sting that you feel on your hand through the glove. Again, the reason for that is you are increasing the amount of time that your glove is impacting the ball. And that is going to mean that overall, the amount of force you have to apply is going to be smaller because the time is larger. So when time goes up, the force goes down because the impulse is going to stay constant. We can use graphical analysis to analyze impulse and change in momentum. So in this graph we have newtons of force on the y-axis and we have seconds of time on the x. And the question asks us basically to calculate the impulse delivered by the force, graphed in the figure to the left between 0 and 5 seconds. So you should basically just think about this as just another graphical analysis question. I have started the process of calculating an area under the curve from 0 to 5 seconds. And I noticed that it is a triangle and a rectangle. So for the triangle, we'll use the equation A equals 1/2 BH, and for the rectangle, you can just do A equals BH. And in case you missed it, the reason why that'll work is because impulse is F net times time. So that's the same structure as the equation for area. So I got 12 Newton seconds in total, 4 by 4 by half for the triangle and 1 by 4 for the rectangle. So 12 Newton seconds is the impulse imparted in those 5 seconds. So we can also use impulse and change in momentum to study acceleration. So we all know that net force is mass times acceleration. And looking a little bit closer, acceleration is change in velocity over time. So I can just replace the A in acceleration with change in v over t, and I can see that F net is m change in v over t. Or you could think of it like this. I'm going to rearrange the equation so that the value for time is on the left-hand side of the equation with F net, and I'll get a new equation, F net t equals m change in v. I also think of this as fat mav. F change in t is m change in v. This was really easy for me to remember when I was in high school because our high school mascot were the Mavericks, and where I'm from in West Virginia, a lot of people have a problem with being overweight. So it was easy to think of it as fat mav. It's not on your reference table, so if you want, you have my permission to use that trick to remember this equation. It will get you out of lots of different binds. Just remember fat mav, and you can use force and time to solve for a change in velocity, or a mass if you wanted to. But if you don't want to remember that, and you have some pretty decent dimensional analysis skills, then you do have this equation on your reference table. J is F net T is change in P, and change in P is really just M change in V. So you do pretty much have the equation. F times T is here, and if you replace the delta P with M change in V, then you have the M change in V part of the equation as well. So we can use this to solve the following question, which states, what is the magnitude of the net force acting on a 2 by 10 to the third, I know it says it looks like 103, but it's really 2 by 10 to the third kilogram car, as it accelerates from rest to a speed of 15 in 5 seconds. So what we have here is we're looking for a force, and we certainly have a mass. We also have a change in V, which is 0 to 15 because it was coming from rest. And we have a time right here. I suggest using fat mav to solve for this. And since we are ultimately looking for the value of force, I'm going to rearrange for that now. And all I really need to do now is plug in values. And finally, just solve. So since I only had one exponent here, I just thought of this as a 2,000 instead of dealing with exponents. So I just did 2,000 times 15 over 5, and I got 6,000. This is a force, so you'll have to report that in newtons. And if they gave me one of the inputs in scientific notation, I need to be prepared to answer in scientific notation as well. I'm getting 6.0 by 10 to the third newtons. And they only wanted the magnitude of the net force, so the direction isn't important here. Alright, conceptual questions, my absolute favorite. In the cartoon below, it is safer to crash into a haystack than it is to crash into a solid wall. And it's similar to the baseball examples from earlier, but basically if you crash into a haystack, what you've got is a very large velocity, but since the haystack imparts force to the car over a long period of time, since it's sort of soft, then you have a large time but a small force. So this is really just the Fat-Mav equation in conceptual form, and it's showing that you can get a large change in velocity if you use a small force and a large time. Contrast that with the same example, where you have the same mass as before and the same large velocity as before, but this time, since you're hitting a solid wall, you are going to have to import a large force in a short amount of time. And that is the reason why the car will crumple, because it's receiving a much larger force than the previous example. So essentially I was using the equation J is F net T is change in P, which is also the same thing as Fat-Mav. And the claim is that the change in momentum needs to be constant. The only thing that can change is whether you're going to do a large force over a small time or a large time over with a smaller force. So it's much safer, by the way, to impart a smaller force over a larger period of time. Similarly, you can use basically the same argument for why a person being punched in the face ought to move his head backwards as he receives the punch, rather than moving his head forward. The reason is, if he moves his head backwards while receiving the punch, then he is increasing the amount of time, which will decrease the amount of force. All right, let's do a sample problem. We have a 5 kilogram object, so there's a mass, with an initial velocity of 8 meters per second. I'll label it VI. And the direction is east, so noted. And we have an unbalanced force acting on the object for 3 seconds. So there's our time, and I'll go ahead and call this F net. I think we're going to have to solve for that. And it causes the velocity to decrease to 2 meters per second east, so that's my VF. And using I'm just looking ahead here, using my VI and my VF, I'll be able to construct my change in velocity. And here I'm asking you to calculate the magnitude and the direction of the unbalanced force F net. So we can definitely use the equation J equals F net T equals change in P, which of course is a region-style version for Fat-Mav. And I'm going to solve the rest of the equation from there using the Fat-Mav equation. I am ultimately solving for the net force, so I'm going to rearrange now to isolate F. And then I'll plug in values. And one of the probably more interesting things I did here was I used a -6 for my change in velocity. And the reason I did that is because initially I was moving at 8 meters per second to the east, and finally I was moving at 2 meters per second to the east. So the actual change in velocity there is -6 as you go from 8 to 2. And this will help me arrive at my answer for direction if I pay attention to that negative positive thing there. So of course this gives me a value of -10 newtons. And the negative in this case does indicate direction, because initially I was using positive values for the speeds in this question of 8 and 2. So getting a negative value is going to be the opposite of, in this case, east. So my final answer is going to be 10 newtons west. Okay, so we also need to understand a very important principle in physics, which is the conservation of momentum. It's similar to the law of conservation of energy, mass, and charge, because it's saying that the momentum of a system has to be constant over time. That doesn't mean that the momentum of an object has to be constant over time. It just means that, like, let's say that you have one object colliding with another object, the overall sum of the momentum before the collision is going to be equal to the overall sum of momentum after the collision. So the overall sum part is referring to the total system, all of the objects involved in the scenario. So the system does need to be considered closed, which just means that there's not other things interfering with the system. So you'll probably see a lot of stuff like that it's frictionless and neglect air resistance and stuff like that. But basically, since the system is going to be complicated, it's going to have more than one object, we're going to use little notes to keep track of the mass of one object versus the mass of another. So you'll see M1s and M2s and so on and so forth. So this is what that might look like. Just consider that you have two objects colliding, so that's why I have two masses, M1 and M2. And since their collision is going to be the exact same length of time for each object, and that's going to mean that the impulse they provide to each other is going to be exactly the same for both. And if the impulse is exactly the same, then the change in momentum is going to be exactly the same for both. If you take that and apply it into a mathematical context, that their changes in momentum will be the same, then you're going to have basically m change in v equals m change in v. This is for object 1, and then this one's for object 2. It is, however, true that they would be opposite in direction. Since they're colliding with each other, the change in momentum for one is going to be equal and opposite for the change in momentum for the other. Or, you could think of it, instead of it being positive equals negative, you could just sort of move them both to the same side of the equation and think of it this way, that the change in momentum for object 1 plus the change in momentum for object 2 is going to equal 0. And this is really a perfect statement of the original idea that momentum is conserved during these collisions. In other words, the overall change in momentum for all of the objects in the system must be 0. Okay, so on your reference table, there's only one equation that deals with the concept of conservation of momentum, and it says that p before is equal to p after. So as simple as this equation is, p before is p after, it really does say an awful lot. It's the most succinct way I can think of really representing the idea that the total momentum of the system has to be the same before and after any event which would change momentum. So I have some conceptual questions to highlight the conservation of momentum that we've been talking about. In this particular diagram, we have a red ball and a white ball undergoing collisions with different circumstances. In the very first example, we have a red ball colliding with a stationary white ball. And what happens is that the white ball basically absorbs the momentum of the red ball. So the red ball is now stationary and the white ball now has all of the momentum. Similarly, the red ball and the white ball in the second diagram are colliding with opposite directions. And after the collision, again, they've sort of transferred the momentum from one to the other. So the white ball is moving to the right when before it was moving left, and the red ball is moving left when before it was moving right. And in scenario C, we have a red ball moving very quickly to the right and a white ball with a smaller speed. And then they sort of trade their momentums again. After the collision, the red ball has the smaller speed and the white ball has the larger speed. So what they're showing overall is that the total momentum of the system actually doesn't change. For instance, in A, we have let's say a positive momentum and 0, and then after the collision we have 0 and positive. So it's still summing to be the same total momentum. So for those first three examples, I said the same thing each time momentum is transferred after the collision. But again, the sum of the momentum is the same before and after. And I find this scenario to be the more interesting scenario, actually. And this is called an inelastic collision. It's referred to as inelastic because these two train cars are going to stick together after their collision, which does change some of our logic. In the first three examples, these were all elastic collisions because they bounced off of each other after the collision, and that's what elastic means, is like bouncy. So yeah, so in the question, or in the prompt, I'm saying a moving train collides with a train at rest. The two trains stick together, and what happens is we have a velocity of 4 initially and a momentum of 0 here in the other car, and then they collide, and then they move off together with a velocity of 2. And the reason for that is because these guys have equal masses, and this one does have velocity and this one doesn't, but the momentum of the system before has to be equal to the momentum after, so basically when these guys collide, their mass doubles, so the speed is going to be halved. And the way I suppose you could represent that algebraically is to think p before is p after, and the p before was the momentum of the first train, which is this guy, and the momentum of the second train, which was 0 in this case. And p before has to be equal to p after, so if we have a mv on the left and an m and a v on the right, but the mass has been doubled because it's two cars that are stuck together now, then the velocity has to be a value 1/2 of what it used to be. That's the only way to keep mv equal to mv. So what do all 4 examples have in common? P before equals P after. And so we have another sample problem. We are going to see a collision here. It's going to be an elastic collision because I scanned ahead and I see that it doesn't say that the two carts are sticking together, it just says that they collide. So we'll keep that in mind later on. But I am going to use M1s and M2s and V1s and V2s to keep things separate. So we have a 1 kilogram cart A, so I guess I'll call that MA. And it's initially at rest, so that is, I suppose, the initial velocity for cart A, so I'm just going to say VIA. It's on a horizontal frictionless air track, so we're neglecting friction. And we have a 0.2 kilogram cart B, so I will call that MB. It's moving to the right at 10 meters per second on the same track. So I'm going to say that's an initial velocity for cart B, so VIB. And it does say that cart B collides with cart A, causing cart A to move to the right at 3 meters per second. So this is a final velocity. I'm going to call that VF, and it's the VF for cart A. So I'm calling it VFA, final velocity for cart A. And they want me to calculate the velocity of cart B, so that would be VFB. So there's a lot going on here. We have a mass for A, an initial velocity for A mass for B, an initial velocity for B, and a final velocity for A, and we're looking for a final velocity for B. So I recommend solving this by using the basic equation, P before equals P after. And in this particular question, the kind of collision we're dealing with is elastic, which means that the carts will be separate before the collision and they will remain separate after the collision. So while the equation that I've just written may seem crazy, I'll try to explain what it's saying. So on this side, you're going to see only initial velocities, and that is saying it's basically referring to the total momentum of the system before the collision. So we have mv, which is the momentum of cart A before the collision, and the b's they're acting as the momentum of cart B before the collision. And when I add the two together, momentum of A before plus momentum of B before, you're going to see that it's equal to the sum of the momentums afterward. But I'm using different variables here. The masses, of course, don't change, but I do have VFA instead of VIA, and I have VFB instead of VIB. But again, what it's really saying is the total momentum of the system before is equal to the total momentum of the system after. And in case you were wondering, yes, I did just sort of invent this equation based on this simple guideline, and the equations may look different in different questions. So be inventive, be creative, and be descriptive with your variables. And lastly, I would say be organized, and you'll have success in these questions. So from here, I just need to figure out what I'm actually solving for. It is VFB, so I'm going to attempt to isolate for VFB now. When you do these isolation procedures, make sure you're following inverse operations and make sure that you're doing PEMDAS in reverse. So I'm going to take care of any addition subtraction first. So that means I'm going to get rid of this term from the right-hand side of the equation. Easiest thing to do is simply subtract it on both sides. So this is my sort of intermediate step, and I am still, of course, solving for VFB, so I'm going to divide by MB on both sides. So my equation looks like this now, where MB is now in the denominator on the left-hand side, and we've reached a point where we can definitely do our substitutions because VFB has been successfully isolated. So I'm going to substitute now, and I am going to be really careful about issues of east and west, because I do see that cart B is moving to the right, and I will probably say that right is positive, so I'll use a positive value for my VIB, which means any other kind of values that come out negative would be west. So I followed through on that. Here is mass A. This is initial velocity of A. Mass B, initial velocity of B, and I chose a positive value, which means that positive is right, and it would mean any negatives would be left. And then I have a subtraction there, so I kept that. And I have mass A and final velocity of A, which is here. And it's all over the mass of B, which is 0.2. And that's going to be equal to VFB. So now all we need to do is solve. So I got the VFB is -5 meters per second after all that. And that, of course, means 5 meters per second left, since I originally said that the positive value of 10 would mean right. Okay, so we're going to do another sample problem now, but this one's going to be for an inelastic collision, so the structure of the problem is going to be very different. We'll start with the usual strategy of labeling values as we see them. So we have a 2 kilogram cart moving due east. I'll call this MA. And again, there's going to be an east-west issue here. And it's moving at 6 meters per second, so that's going to be my VIA. It collides with a 3 kilogram cart, so it's going to be my MB. Moving due west, so here's my east-west issue. I'll have to be careful about positive and negative. The carts stick together, and this is what makes the question inelastic. And I'm going to call this MA plus MB. So it's MA and MB once they stick together. And they come to rest after the collision. So that's going to be my VF. I guess I could say VF A plus B, but I'm just going to say VF and try to keep it a little more simple. And I do want the initial speed of the 3 kilogram cart, so that's VIB. And let's start this with a very simple equation of P before equals P after. And in this next step, I get to be creative. P before is the total momentum of the system beforehand, and essentially it was cart A moving east at 6 meters per second collides with cart B moving west at some speed I'm not sure of. So I'm going to say that's just MA VAI plus MB VBI. So there's the total momentum of the system before the collision. But after the collision, everything's different. The two carts stick together, and of course, since they're sticking together, they have the same speed. So I'm going to represent the right-hand side of the equation very differently. I'm just going to say ma plus mb, and I do need to put it in parentheses because I'm going to move these guys around together since the carts are sticking together. And they're moving at final speed, which is the same for both, so I'll just say VF. Now, what I'm actually solving for is VIB, the initial speed of cart B. So as I isolate that, as a preview, I'm going to subtract out MAVIA, and I'll put it on this side with a subtraction. And then I will divide out the MB to isolate VIB. So here's my intermediate step, and I have subtracted MAVIA from both sides. And I just need to do one more thing, which is to continue isolating VIB by dividing MB on both sides. And so I executed that isolation of VIB, and the equation is now finished and it's ready for substitutions. So I'm going to go ahead and do that, but as a preview, I will point out that there is the east-west issue, so I'm going to use positive values for VIA, which will mean east, and then negative values will mean west. So I plugged in, I used a positive value for the initial velocity of cart A, so I just need to solve now. So I got -4 meters per second, which of course would mean 4 meters per second west. Alright, we did it. You've reached the pair up, so I will have photocopies of this pair up and this pair up ready for you when I see you next. But I do need you to copy down these summary questions underneath the do now questions and the aim on your classwork sheet for this lesson. So copy these guys down and then you'll be done. Thanks for watching.